Here we go. We have a question trapping rainwater. So it's a hard level question and you have given an array with non-negative integers representing the height of blocks. If the width of each block is 1, compute how many water can be trapped between the blocks during the rainy season. So we have given this example and it is illustrated. Then we need to find the total water trapped between the buildings. So this is not a good visualization. So let me, yeah, so this is a good example. So water can be stored here and here and here. It means between the buildings. So now let's come back to this example. We have this and 3 water can be stored here, 2 here, 3 will be here and 2 here. So the total water is 10. And in this example, the maximum water can be stored is 7, means the total water. And in this 0, in this example we have 9. So you can calculate it, but I'm not gonna like represent and make the diagram. I will stick to one particular example. So this video can be a bit lengthy. In this video I will tell you 4 different approaches that you can apply for this question. Now let's try to build an approach. So we have given this example. So suppose we need to find how much water can be stored at this position. So at this position the maximum water can be stored. So we have this much length and this is the left boundary, this is the right boundary. So it will be the minimum of left boundary or right boundary, and this particular thing can be applied at any on every index. So the formula is minimum of left boundary and right boundary, but this is not correct. Suppose we are at this particular index, so its left boundary is this, its right boundary is this, so it will be the answer will be 2, but one length is already occupied by the block. So minus, we need to apply minus height of the current building, height of ith building, and so this will be our formula. Now let's try to find out the left boundary and the right boundary. So we have a left array. For this particular index the left boundary is 0. On this particular index it will be 1. On this particular index it will be 1. On this particular index we don't have any left boundary, so you can store indices or you can store values, whichever you prefer. So we have in this I'm gonna apply 4 approaches. So in one of the approach I will take indexes, in another approach I will take the values. So now let's consider the values. So at here the maximum height or the maximum boundary will be the current value. Here it will be the current value, and here it will be the current value, not current value, it means the left boundary, which is the maximum left boundary. On this particular index we have this value, so the value is still 2. On this the value is 3, and on this the value is 3, 3, 3 and 3. So you can store values or you can store indices. So we have built the left array. The same approach will be applied to find the right array. So at this position the value will be 1, at this position the value will be 2, on this position the value will be 2 itself, because this is the right boundary. On this value the right boundary will be 2, on this it is 3, and every value will be 3. Now let's find out how much water can be stored on every index. So let's start with this index. So how much water can be stored on this index? So this is the formula. Minimum of left boundary or right boundary. The minimum will be 0 minus height. So it will be 0. Yes, it is true. The value is 0. On this index, how much water can be stored at this index? So on this index, the amount of water, the minimum of this value, so it will be 1 minus 1, so 0. Now we have this index, so the minimum value is 1 minus the height. So height is 0, so 1 minus 0 is 1. So 1. On this index it is 2, so 2 is the height, so 0. On this index the minimum is 2 minus height, so it will be 1. On this index the minimum is 2 minus height, which is 2. So same applies on every single index. So 1 here, 0 here, 0 here, 1 here, 0 here, 0 here. So one way to solve this question is using this approach, or another way. So another way can be to use a stack. So first of all, now let's stick with this particular approach. So let's code this. So we have this. We have n left and right. We have an array. If the previous index is not accessible, just pick 0. So find the maximum between 0 or the current length. So the value will be current, means ith element, or we are at a index which is not equal to 0. So then we're gonna compare with the previous index, means the previous value or the current value. Same applies for the right hand side. We are starting from the right hand side. So same applies here. If I plus 1 is not accessible, just take 0 and find the maximum between 0 and the current element. Then we have this for loop, and in this we have minimum between left and right height minus current element, and return the answer. So it will work. And in this, the time complexity is order of n, space complexity is order of n. So we have solved this question and it will work. But one thing, we can solve this question using stack also. So now let's erase this. So we have this array, and for this particular position we need to find the left value, which is the maximum value. For this the value is 2. The value is 2. Although we have a value which is 1, but we're gonna pick 2 because this is the maximum. We need to find the maximum value on the left hand side for the left array. So now let's focus first on the left array. For this we don't have any left value which is the most greatest value. On this we don't have any value, so this will be the current value. For this the value will be this. For this we don't have any value, so this particular index will be the maximum value to himself. For this the value is this. For this the value is this, and not this value. Why not this value? Because if we pick this value, then we need to find the minimum value between this and this. So that's why we need to consider this value and this value. So for left we're gonna pick this, not this. So we're gonna pick the left, the maximum of left value. For this the maximum of left value. For this the maximum of left value, if we don't have any value, so now every value will be this. For this the value will be this. For this the value is not this, not this, the value is this. So now let's take a stack and we have left array. So I will call it L for this particular index. What's the left side? Our stack is empty, we don't have any left side. So the value, this particular value is the maximum value till now. So we're gonna add 0 and we're gonna need to store the index. Next we have this. So what's the maximum value on the left hand side? The maximum value on the left hand side, uh, so we have this index and the value at this index is smaller, so we're not gonna pick this. So the value at this particular index is smaller, so we will pop out this value. And as our stack is empty, so this is the maximum value we gonna need to place the index. Then we have this. So the value is 0. So value at this particular index, is it greater? Yes, it is greater. So we're gonna pick the value at this particular index. Then we will not add the current element. We will not add the current element because we have a decline here and we want the value to go like this. So that's why we not gonna pick this value. So then we have this. Is the value at this particular index is greater? No. The value at this particular index, which is this, is 1, which is less than. So that's why we will just erase it, and as our stack is empty, so just push the current index, current index, current index. Then we have this. So is the value at this particular index is greater? Yes. So we will just take the index. Then we have this. So just pay attention, this is the crucial point. So we have this index. Is the value at this particular index is greater? Yes. So we're gonna need to pick that index. So as you can see, we will not add the index 4. So if we have added the index 4, it will pick the index 4. But the real index, the leftmost maximum value is this, the value 2 at index 3. So we're gonna pick 3. So that's why we will not add the decline path. Next we have 5. So the leftmost value is at 3. So then we have this. Is the value at this particular index is greater? Yes. So we're gonna pick that index. That index, yes. So then we have this. Is the value at that particular index is greater? No. The value is much smaller. So we will remove it. Now our stack is empty. So we're gonna just place the current index. Same for this. Is the value at that particular index is greater? Yes. The value at 7 index is greater. And the value will be this. Now let's find for the right array. First we need to clear out our stack, or you can take another stack, but I prefer to clear out the same stack. So our stack is empty. So the rightmost maximum at index 11, at this particular index, is the index at this position is greater? No. So just remove it and consider the current index. Next we have this index. Is the value at that index is greater? Yes, you can verify it. It is greater. So just take that index. Is the value at that particular index is greater? No, it is not greater. So just pop out, and so we have same value. So you will pop out the value. So then we have 8, and then we have 8. Then we have this index. So is The index at that particular value at that is the value at that particular index is greater? No, the value is smaller. So we will pop out and insert the current value, insert the current index, and all the values on the left hand side will be 7. So then we have this. How it is useful? So now let's check. First, we have left and right. We have left and right. So it means our stack is empty, and 1 second. So how is the left array and right array is useful? So for let's suppose we have this index, and it means the left index is 3 and the right index is 7. So we're gonna pick the minimum between these two index values. So we have either value 2 or we have either value 3. At index 3 we have value 2, and at index 7 we have value 3. So we're gonna pick the minimum between these two. So the minimum, it will give us uh, like a surface. So we have minimum this. So at that, to that length we can store the water. So as we have already discussed, so we're gonna apply this formula: minimum of left boundary or right boundary minus height. Now let's run this. We have this first. First we have this. So it means the left is itself and the right is 7. So we're gonna pick the minimum between these two. Minimum between 0 or minimum between 3. 0 and 3. So we're gonna pick 0. And the height is 0. Height is 0. So 0 minus 0 will be 0. The value is 0. Then we have this. So it will be minimum between this and this. So it will pick 1. So 1 minus 1 will be 0. For this, the minimum at this index and a minimum at this index. So the value is 1 here, value is 3 here. So we're gonna pick 1. So 1 minus height. So it means 1. And this index, at this index, so let me change the color, 0, 0, 1. And next we have this index. So we have 3 or we have 7. So we're gonna pick between 2 and 3. So the value is 2. So 2 minus 2 is 0. And the value at this index is between 3 and 7. So we're gonna pick 2. So 2 is the minimum between this value at this index and the value at this index. So we're gonna pick 2 because 2 is the minimum minus height. So 2 minus height is 1. So then we have either 3 or either 7. So we're gonna pick between 2 and 3. So we're gonna pick 2. So 2 minus height is 2. So as you can see, it is giving us a correct answer. So it will work, and so it will give us like this, and we just need to find the total. So 1 plus 1, 2, 3, 4, 5, 6. So the answer is 6. Now let's code this. So we have this left array, right array, and the stack. So while we have uh, element on top of a stack, so this is the index, and the element at that particular index is smaller than the current element, means current element is greater, so it can become the left boundary. So just pop out the left side elements. If stack is empty, just push the element, otherwise no need to push the element. So this is the only case, and we just need to find the left boundary. Just clear out our stack. Same applies for the right side. So same applies for the right side. Code is as the same. We just have a right array instead of the left array. Then we just need to do the third iteration. Find the minimum between index on the left side and index on the right side. So take the uh, just take the indices and find the corresponding element minus the current height. So it will give us the height. Just consider the height and return the answer. So it will also work. And in this, the time complexity is order of n, space complexity is order of n. One can argue that we have for and while loop, but still it will be order of n. So we have this. On the worst case, you can go to like 2n, but it will not go. So we have solved it. And in the second approach, we have done this by using left and right array only and not taking stack. So you can still optimize this. We have left and right array. So if you clearly observe, our first iteration and third iteration is kind of same. So we just need to find the left array, left elements. So you can do this on the go by iterating from left to right. We are iterating from left to right. So why not do the left side on the third iteration? Why not find the left elements, the left maximum elements in the third iteration itself? So yes, we can do this. Let me show you the code. So we have this code. So this is the maximum and this is the minimum. We don't need left array. The left variable, only left variable will work. We just need to find the maximum of the left element and the current element. So we have this and this. Just take the value. So this is exactly the same, but in this case we still have time complexity order of n and space complexity order of n, but the expected space complexity is constant. So we have to find a way to like reduce the space complexity. So now let's observe something. We need to find the left boundary and we need to find the right boundary. Can we do this by using two pointers? Let's find out. So we need to find the left boundary and the right boundary. Or we can say left max or right max. So this is our L, this is our R. So we have this and this thing. And we need to find the left boundary and right boundary. So we can say it left max or right max. Maximum between left max and right max. Yeah. So we have left and right. So which value is smaller? The element on left or the element on the right? Yes, the element on left is smaller. So what we'll do? So we have left and right boundary and we also need to find the boundary itself. So let me call it left maximum. So the left maximum will be our current element, the maximum. So let me write it here. Left maximum will be the maximum between already left boundary or the current element So in this case the left maximum will be our current element, and we need to find how much water can we store. So the formula is left boundary or right boundary minus height. So isn't are we sure that our left boundary is much smaller than our right boundary? Yes, we can say it. Our left boundary is much smaller, or we can give it surety. So our left boundary is smaller. So the formula will be this: left boundary minus height on current index, or let's say L. So I am just taking this and this because we know our right maximum is already smaller. Although you can write this thing means the maximum between the right max or right or left max, but we are sure that our left max is much smaller than our right max, so that's why we can write it here. So now let's jump to next index. So we have this and this index. Is the elements is our left hand side smaller? Yes. So our left maximum will be this. And how much water can we store at this particular index? Means the left max, which is 1, and minus current, so which is 1, so 0 water till now. Let's move our pointer. So now we have this index L. So is our L smaller than right? Yes, our L is smaller than right. So how much water can we store here? First of all, find your left boundary. So left boundary will be here, and we will not gonna update our left boundary. And the water can be stored is left max means 1 minus 0. So 1 water can be stored here. So we have filled it. Let's jump to next index. So we have this. So this is crucial point. So first of all, is our left smaller than right? No, our left is not smaller than right. So we need to update our rights. So we have right boundary also, right maximum, right maximum. So the code will be same, right maximum will be maximum of already right boundary or the current element and find your answer using this thing, right max, because we are sure our right max is smaller, minus a of r. So yes, and how much water can be stored at this particular position? So our right max is this, and right max is 1 minus r's value is 1. So the value is same, no water can be stored at this position. Update your r because our r's value is smaller, so that's why we need to update our r. So in this case our left is smaller, so we have this condition. Find your left boundary is this, but this is much smaller, so we will update our left boundary or our left maximum. How much water can be stored at this position? 0. Jump to next position. Then our left hand side is still smaller than the right. How much water can be stored at this position? Right max 2 or 1? 2 is maximum, so 2 minus 1, 1 water can be stored at this position. Yes, this is correct. Jump to next value. How much water can be stored at this position? Left hand side is much smaller, and find your left boundary at this position. So 2 minus 0, so 2 water can be stored at this position. We have next index, so this value is still smaller than this value, and our left boundary is this. How much water can be stored? So it will be 2 minus 1, so 1. Jump to next. We have this L and R, which is smaller. Our R is smaller. Find the right boundary. Right boundary will be this. How much water can be stored at this position? 0. Jump to next value. How much water can be stored at this position? Our R is smaller in this case. So find right max. So our right max will be this. So 1 water can be stored. Jump to next index. We have this. In this case our right is still smaller, so the maximum is 2. So 2, either this 2 or this 2, so just change it whichever you prefer, but the value we are not storing the index, we are storing the values. So we have 2, so 2 minus 1, 2 minus 1 is 1. 2 minus 2, actually, yeah, 2 minus 2 is 0, so we have 0, and we have this index, so now it is same. And that's all. The water can be stored is correct. Yeah, this is correct. Let's code this. So we have n, l and r, left max, right max, answer. If our left hand side is smaller, so just take the left boundary and find the water stored on the lth position. Increment your L, as our right hand side is smaller, so we have a right boundary, so this will be our answer, and the water stored on the rth position is this. Update your R, return answer. Let's submit this. In this case our space complexity is constant, and this is the expected approach using left boundary and right boundary as a variable, not an array. Thank you all for watching.